Introduction to Space Plasma Physics. We'll talk about the scope, history, and relevance. These are the learning objectives. We see by the end of this lecture, the student will understand the concept of space plasma and the scope. We will be able to distinguish between an ordinary plasma and a neutral gas. We will also list some of the major plasma regions in space plasma. We have a few slides regarding the historical development of this field. Then something regarding the fourth state of matter, that is why we call it a fourth state. And at the end, we'll try to discuss the scientific and practical importance of studying space plasma. The course book for this semester regarding the space plasma physics course will be following the Bohm-John famous book on basic space plasma physics. Okay, let me tell you that in today's lecture, we don't have any mathematical derivations or technical concepts. Since this is an introduction, so we'll be only focusing regarding the main points that we will be focusing in this course. Okay, so space plasma physics is the study of ionized matter in space. By space, we mean just outside our atmosphere, right? So once we are out of our atmosphere, ionosphere, magnetosphere, the interplanetary space and beyond, the matter exists in ionized state. So that's where the space plasma physics is relevant. Okay, it deals with the behavior of charged particles such as electrons and ions, since the matter is in the ionized state. So electrons, ions, and dust particles are there. So their dynamics are relevant once we are talking about the space plasma physics. Okay, since these are charged particles, so these particles interact through the electric field, magnetic field, and it gives rise to collective effects. Those will be our main concerns in this course. Now, the space plasma physics covers plasma environment around the sun, the planets, moon, comets, and interstellar space. As I told you in the first bullet, that these areas of our space, so there we will be talking about plasma and the particle dynamics. Now, it connects the plasma physics with the astrophysics, the space science, and the planetary science. So this is a comprehensive course where we'll be talking about the particle dynamics, and this lies in the regime of astrophysics. We call it a space science, and sometime when we are doing planetary descriptions or particle dynamics, so we call it a planetary science. Now, these are those regimes where plasma physics is relevant. So we need to know what is actually a plasma. Plasma is a partially or fully ionized gas. That is, it is a high energy state of matter. It contains basically electrons, ion, and sometimes neutral particles. They are different than the ordinary gas. So plasma responds strongly to electromagnetic field. We know that gaseous state matters interacts mutually through collisions. So once those collisions are replaced by electromagnetic interactions, so then those gases are known as plasma state. Now, because the interaction is collective, so we call it plasma often behaves collectively rather than isolated particles. Because of these particles, these properties, plasma show many phenomena not seen in the solid, liquid, and neutral gases. That's why we call it a independent state. Sometimes we call it a fourth state, because it requires a completely new descriptions for the particle dynamics. So that's why we call it a fourth state of matter. So over this slide, we have seen that where the space plasma physics is relevant, and also to understand these regions, the particle dynamics in astrophysics or the planetary sciences, we need to know the concept of plasma, and plasma is nothing but the interactions of electrons, ions mutually through electromagnetic fields. Now we move towards the next slide, which is about why is plasma called the fourth state of matter. As I told you, that it requires a completely new descriptions starting from the solid, liquid, gas. So that's why this is a fourth number. So we call it the fourth state of matter. In solid, particles are tightly bound. In liquid, particle moves freely but remains closer together. So those two requires independent descriptions to describe the particle dynamics. In gas, uh, particles are free and mostly neutral, but in plasma, enough energy is supplied that atom lose electron. So if we see from solid towards plasma, every time energy is given and some sort of a bond or interactions is liberated in the form of energy, so that once we have the atomic state, or we call it a gaseous state, so there the atoms are neutral and they are bounded, that is the electrons and the nucleus is bounded by the Coulombic interaction. So if we give energy to the gaseous state atoms, it will be ionized and it give rise to electrons and ions, that is we ionizes the atoms in the gas and we move towards a new description, which is the fourth state of matter, we call it a plasma. So as a result, a gas becomes an ionized medium of charged particle. So if we move from solid to liquid, then gas and plasma, so we are at the fourth position. So that's why we call it a fourth state. Or we can say that a fourth independent description is required, so that we call it a fourth state. Okay, I told you this, that from gas to plasma, if we move uh, from gas to plasma, when a gas is heated strongly or exposed to energetic radiation, ionization occurs. This is already told to you. Ionization means electron is removed from the atoms or molecules. The results is in the form of electrons and positive ions. If ionization is sufficient, gas enters the plasma state. So this is a technical term that we cannot always say that anything inside the gas in the form of ions and electrons, we call it a plasma state, but there are some technical criteria for the gas having ionized state of matter, then we term it as a plasma state. So in this course, in the first part of the course, we'll be trying to focus on those criteria for the generation, or we can say that for the creation of the plasma state. In space, since this course is not about the plasma in general or the laboratory plasma, this is dedicated to the space. So that's why in space, ionization is commonly caused by solar radiation, particle impacts, and shock heatings. So, like we already discussed in the previous course in the BS level, at the BS level, that for the plasma to create, we need some sort of energy so that it creates or it generates the plasma state. So in space, that energy comes from the solar radiation and particle impact and also shock waves. We will be focusing on these phenomena in this course. Now, once we are in a position to understand the plasma state, then some basic characteristics of the plasma, that is the presence of free charge particle, that is the first ingredients required for a gas to be termed as plasma. Now, once we have charged particles, these charged particles cannot be influenced by any mechanical force, so strong response to electric and magnetic field. That is, charged particle can only be influenced by electric field and magnetic field. So fields are necessary ingredients as well once we are talking about plasma dynamics. Ability to conduct electricity, since once we are talking about charged particle and they can be manipulated by electric and magnetic field, so it will give rise to electricity, and then we'll be talking about electric conductivity and regarding those terms. Now, collective behavior due to long-range electromagnetic interactions. I told you that plasma composed of many charged particles, electrons and ions, and they interact collectively. That is, individual interaction is quite rare to deal with. So then in those cases, we are left with collective behaviors. Now, this charged particle when move, it supports various type of waves in stability and nonlinear structures. As I told you that charged particles when move, it can give rise to electromagnetic waves, and those electromagnetic waves coupled to give rise to instabilities and nonlinear structures. Now, the occurrence over a wide range of densities and temperature. Now, this is one of the fundamental characteristic of the plasma, that the characteristic of a plasma depends upon the density and temperature. So we can say that any plasma is different than the other plasma regarding their densities and temperature. So once the density and temperature changes, the properties or the characteristic of the plasma state changes. Okay. Now, if we compare the ordinary plasma state with a gas, so we can say that ordinary gas is mostly neutral and weakly affected by electromagnetic interaction. Weakly affected because gaseous state matters are mostly neutral and they are interacted through the collisions rather than electromagnetic fields. Plasma contains charged particles, so they will obviously be influenced by the electric and magnetic field. Gas collisions dominate many neutral gas. This is already understood to us. In plasma, collective electromagnetic interaction can dominate, and plasma can support oscillation and waves then that neutral gas cannot. So these are the fundamental features which one need to know to differentiate between a plasma state and an ordinary gas. Okay, so once we are in this position that plasma is mostly composed of charged particles and they move collectively or interact collectively, they can only be influenced by electric and magnetic field. So now we are moving towards our universe. Where is this plasma state? So plasma is most common visible state of matter in the universe. That means most of the matter exists in this plasma state. Just outside our atmosphere, everything is almost in the plasma state. The sun, the star are made up of plasma. These are high energy states of matter. Once we have charged particle governed by the fields, so it gives rise to this state. The solar wind is a plasma outflow from the sun. That is, whatever energy coming from the sun to the outer space, to our solar system, and to the surface of the earth, it always comes in the form of solar radiation. And these solar winds mostly absorb in different layers of the atmosphere, and we receive only the visible part of the energy from the sun. But the source of that energy is plasma inside the sun. Also, the planetary magnetosphere and ionospheres contain plasma. As I told you, most of the energy is absorbed in the outer or the outer space layers, such as planetary magnetosphere. That is in Earth-like planets. If we are focusing only on our planet, say the Earth is having a protected magnetic field, so that magnetic field actually traps the solar wind and just to protect the habitation on the Earth. Similarly, some of the energy is utilized in ionizing the top layer of the atmosphere, so it is termed as ionospheres. The interplanetary and interstellar medium also contains plasma. So this first bullet is basically reflected in the rest of the bullets, that most of the state, most of the visible universe is in this state. Okay, major region of space plasma physics. So these are some terminologies that we'll be focusing right throughout the course. Solar corona, solar wind, those are the terms associated with the solar energy. The interplanetary medium, that is within our solar system, we have different planets. So in between the planets, we have medium. Those mediums are part of the space plasma physics. Magnetosheet, magnetosphere, these are the terms we'll be focusing once we are move towards the technical part of this course. Okay, so these are example of space plasma. As I told you, solar corona around the sun, solar wind flowing through the helisphere, the Earth ionosphere and the magnetosphere. These are all various space plasma regions where the space plasma is relevant. And there the particle dynamics and the field profiles can be checked, or we can say can be estimated and can be described with the help of these plasma physics theories. Now, why plasma physics is special? These space plasmas are often very large in size. As I told you, it is like infinitely extended. Once you are talking about laboratory plasma, so there we have the plasma exists within the chamber. So chamber is mostly say around 10 meter. But when we are talking about space plasma, so they are very large in size. They are usually low density compared with the laboratory plasma. So low density means collision-less plasmas. So magnetic field often control the particle motion. As I told you, the Earth is having a magnetic field, protected magnetic field. They can be influenced to control the motion of the plasma particle. Once the density is low, so we can say that the plasma is collision-less. Many observed structures are governed by wave shocks and instabilities. These are the three collective uh, behavior signatures in plasma. For example, if a particle moves collectively, it gives rise to different kinds of electromagnetic interactions. We call it waves. It can couple to give rise to shock waves and also instabilities. By instability, we means free sources of energy that can influence the particle motions. Now, these particles in space plasma regimes have this low density profiles, but these particles can be influenced with the help of electric field and magnetic field. Charged particle experiences the Lorentz force. That is, it is influenced with the help of electric field and can be influenced with the help of magnetic field. By electric field, we means it will accelerate the charged particle and the magnetic field will gyrate the charged particle. So these are the standard forces that the particle experience. By particle, we means charged particles. Now, since we know that inside the plasma we have large number of charged particles, so that individual particle dynamics cannot be tracked. So plasma does not behave only as a separate particle, but rather they can be influenced collectively with the field profile. Okay, so just a historical background. So we know that some of the observation in space like auroras, solar activities raised question about the charged particle in space. So these are uh, some of the observation, or we can say that the observation which can be viewed from the surface of the earth. So these are some of the, we can say, basic motivations for the field to start with, and now it is now a well explained and well explored regions. some of the key milestones that people are achieved over the last few decades. So we can say that aurora, geomagnetic phenomena, development of the ionization theory and plasma concepts. So that is, we have observation, we have theory for that. And recently, we have satellite exploration of the planetary magnetosphere and ionosphere. So these are the various milestones that we achieved. So all these will be part of this course. The space age and the plasma discoveries. So we know that before satellite, many space phenomena ideas were theoretical. As I told you, like the case of auroras, those are the direct observation from the surface of the Earth through the polar regions of the Earth. Spacecraft allowed direct detection of the particle field and waves. So over the recent times, we can say that from the 1980s, we call it as era of satellites. So then those particle or those fields can be detected directly through those satellite missions. And we have various terminologies that now well explained with the help of particle dynamics. Now, some scope of the course that fundamental plasma concept will be discussed. Those plasma concept in the form of charge particle motion, plasma, how we describe the plasma. So we need to describe it as a fluid description. If we have a describing it over a large time scale, so we move toward the magnetohydrodynamic theory, and all those things will be described in the Earth atmosphere, around the Earth atmosphere, in the planetary regions. We'll be applying those theories to understand those regimes. Okay, so sometime we need to understand the various concepts, for example, to explain the space weather disturbances, to protect satellite and communication systems, to understand the auroras, the magnetostorm, the radiation belt. These are the things which need to be explored before it can damage various space-based technologies. The main thing in this course is focus on the space plasma physics and space weather. Solar eruptions can disturb near Earth plasma physics, as I told you. The space-based technologies can be protected with the help of these auroras, these magnetostorms. This is also relevant with the different planets, since we know that over the last few decades, people are talking to move some of the habitations toward the Venus or Mars. So we need to explore these other planets within our solar system so that habitation is possible or not, or we can say that why, for example, we don't have a protected magnetic field, or we can say a strong magnetic field around the Venus. So there, in order to understand all these phenomena, these astrophysics is relevant, and we need to discuss these things as well. Some modern technologies, satellite operation depends on space plasma conditions. Spacecraft charging is a space plasma related issue. So we'll be focusing all these in these courses and to lift with these questions. This is the last slide. Important question to space plasma physics. That is, how is the solar wind accelerated? With the help of those fields, self-generated E field and B field, how do shock form in collisionless medium? How are particles heated and accelerated? How does wave transfer energy through plasma? And how does magnetic field control the plasma transport? How does solar activity affect the planetary plasma environment? So these are various questions that we can answer in this course over the last, we can say, over the coming 30 lectures. So that's it. This is all about a brief introduction of the course, what is on offer in this course, and how things can be understood with the help of this tale.